Um, I can't divulge that, but the highest grade in class was an 88, and you know who you were, or are, I should say. That was the highest grade in the class, was an 88. So, based on that, and don't think I'm going to do this the rest of the semester, but because it's the first test, and maybe I should have given you some more time, I put curve on that. So I thought I was very generous. So whoever got the 88 now has a 100. So you know who you are, Miss 88. So now you have 100. So do the math. Everybody got a 12-point curve on this. That ain't going to happen again, folks. And again, I warned you that the summer is tough. You know, I understand, you know, when the summer things are busy, you want to go on vacation or whatever. Some of you have jobs which are obviously interfering as well. I've had more than one student that said they tried to take their test while they're at work. That's crazy. I don't even know what boss would let you do that, but that wasn't the intent for you to take your test at work and then have something happen. Okay. So, and again, and we're starting fresh. Please have pen and paper or pencil and paper and write down what I tell you is going to be on the test. Good gosh, what have I said at least 20 times about stuff that's in green? Verbatim. Yeah, and several of you didn't do that, and I don't know what's going on there, you know? So when I say it's verbatim and I say it's going to be on the test, you should have been writing that down. There should have been no surprises on these two exams. The second one looks better. I'm not finished yet because it can be long. It takes me longer to grade them than it does for you to take them. But they look better to some extent. Looks like some of you did run out of time at the end, even with an extra 20 minutes. But again, some of you need to learn, and this is science. This is how scientists work, is make your answers short and sweet. This is not an English class, so you don't need to use, you know, all the proper grammar, just a bullet statement for stuff like that. So anyway, and I think what I'll do, because I'm concerned, some of you, you know, even with 12 points, you're in the hole. Like I said, I haven't finished grading the second exam, but I'll have that done quickly because I want you to know where you stand before the next one. Okay? So, with that said, we will press on. So, are we ready? All right. Reset, clean slate. Here we go. All right. Dun, dun, dun. So now we're on to it might be my favorite system. Because I'll explain that. What? Yes, making me. So Christine bought new green pens. Very good. Can I record? Okay. Oh, say Tuani said please. So, okay. Since looks like we have a dedicated class here, we still have 20 students. So I will indeed. Okay, fine. I'll record as long as we keep up with the full 20 people in the class. I'll record them because I know hearing it a second time definitely helps. So I will record. Boom. All right. As long as we keep our numbers up. All right. So that we're off to the respiratory system. And I guess one of the reasons I really like the respiratory system, because this was a big part of my job when I was an aerospace physiologist. Because as you know, there's no air in space or at high altitude. So I had to train astronauts and pilots how to deal with, their life support equipment, their oxygen mask and all that stuff, and explain what's going on there at high altitude at the physiological level. So it's kind of cool. So good news, respiratory system has very little anatomy. All right, very little. The lungs are pretty darn simple if you think about it. Bad news, the physiology is pretty intense. And so, like I said, folks, you need to find that time to study. You got to find it. All right. So the respiratory system is probably more complicated than the heart. So find the time, please. I want you guys to do well, but if I tell you something's going to be on the test, and then when I grade your test, and I'm like, geez, I told them this was going to be on the test, that tells me you didn't find the time to study. So with that, I'll quit whining and carping, and we will start our new material. So let me get this straight up a little bit here. Boom, 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 boom. Just give me 1 second. It's not quite lined up like I want. All right, that should work. Okay, so the respiratory system, we're going to break this down into several phases here. For respiration, we have pulmonary ventilation, and that is just the mechanical getting air in and out of your lungs. That's all ventilation means. Then we have external respiration, which is kind of misleading because it's still inside your body, but it's the gas exchange between the lungs and the blood or the capillaries. We'll talk about how we get O2 to the tissues and CO2 to the lungs. And then internal respiration. Well, Suresh, reboot. Yeah, we should all know that by now that, yeah, if I'm coming off choppy and whatnot, just reboot. And that should do the trick most of the time. Everybody else got me 5 by? Okay, good. All right, so, and then we have the internal respiration, which is the gas exchange between the blood vessels, the capillaries, and the actual tissues. All right, so we're going to take a systemic approach to this. So we're going to cover the anatomy. The anatomy is pretty straightforward. Listen to me carefully. Does everybody have their pen and pencil ready? So one of your big questions on your test is to describe the changes in the mucosa. If you recall from way back when in AMP1, the mucosa is the inner lining of your hollow organs. So what I mean by describe the mucosa for respiratory, you're going to tell me the changes in the epithelial tissue for the most part, from the nasal cavity all the way to our alveolar sacs or alveoli. All right. So some of the stuff I'm going to go through quickly because it's like, okay, yeah, no kidding. All right. I'm not going to make a big deal out of it. You can study that. All right. So here's one of your basic AMP, or excuse me, I should say anatomy slides. Very simple. Like I said, the anatomy is pretty simple. That's why I'm going to make a big deal about the epithelial changes. So we include the nasal cavity because we do use that to breathe through. Me, not so much. I've had my nose. I was a big baseball player. I don't know if I ever mentioned that. So I've actually taken 3 shots with a baseball to my face twice while I was batting. And yeah, one time I got a full 90-mile-an-hour fastball right in my face, and it literally pushed my nose underneath my right eye. It took 3 surgeries to get it back where it was supposed to be. So yeah, it was ugly, but yeah, lots of surgeries. But I remember waiting to go into the surgery, and I looked at my nose, and yeah, college ball. I looked at my nose that I looked like Quasimodo or some ogre, because my nose was, by that time, was swollen like a full-on pig nose, and it was underneath my right eye. And I'm like, oh my God, I am deformed. But they fixed it. They fixed it. Anyway, so I can't really breathe through my nasal cavity, but some of you can. Yeah, like Baltimore. Thank you, Cindy. All right, here we go. So we have the basic components that we're going to go through in greater detail here. But again, as you can see, the anatomy is pretty straightforward, and we'll get through this in a little bit of detail. So again, some basic stuff about the muscles. We have the diaphragm. That's that flat sheet of muscle right underneath the lungs. And I'll explain exactly how that works a little bit later. And then you have these, and you should have learned this from AMP1. You have your internal and external intercostal muscles. And again, when they contract, they kind of lift your rib cage up, and the diaphragm contracts and pulls down. And so here's the question. You know, I'm probably dating myself, but there's got to be some of you that know what a bellows is. Who knows what a bellows is? Jessica doesn't know what a bellow is. Oh my God. Andy, you don't know? I am shocked. So you guys never seen an old school fireplace that had the thing that you would open and close and squeeze and it would blow air into the fire? Is that? Okay. All right. All right. Okay, so we'll save that for a little bit later. But yeah, Google bellows. It's just a little like an accordion, and you have little handles, and you expand it, and it sucks the air in, and then you compress it, and it blows the air out into your fireplace to get the fire going. Anyway, that's basically how your lungs work, and we'll talk more about that later. So I know you're getting old when all your references are things you folks have never seen or heard of before. All right. Okay, so when we look at the respiratory system, we have the conducting zone. That just means the air passageways. And we start, we can start wherever your nose or your mouth, and we work our way to our trachea, what you guys have basically known as your windpipe. And then we have branching and branching and branching. And this is pretty amazing. There are 23 orders of branching in the lungs. Now, we don't count them all, but by the time we get down to what we call the alveoli, the little tiny little air sacs, we have increased the cross-sectional area and the surface area to such an extent that if you took every one of your little alveoli and you peeled them and flattened them, like an orange peel or something, and you laid them across a tennis court, it would cover almost the entire tennis court. So again, extraordinarily efficient, extraordinarily efficient. And so you have about 300 million alveoli, and again, that provides you with all that surface area for gas exchange, O2 and CO2, which again, pretty much covers a tennis court. I'm not going to ask you anything about the nose except for one or two things, all right? Because this should be straightforward. We have our nasal cavity, and when we inhale through our nose, the benefits of that is to moisten and warm the air so it doesn't shock the lung tissue. Also, we filter the inhaled air. So if you breathe through your nose, you're going to trap a lot of the particles, the pollen, the dust in the mucosa, because it's got these little cilia and whatnot. And then you get rid of it. Guess how you get rid of it? All the stuff that you trap in your mucosa, in your respiratory pathway, how do you get rid of it, somebody? No. That's a good guess, Nada, but no, not sneezing. No, no. Anybody else? No. Well, you could, but that's not how you normally do it. You're inhaling stuff all day long. All right. And you got a lot of stuff that's trapped in the mucus in your nasal cavity. So, okay. Poop. Okay, you guys. Okay, you can pick your boogers. That's it. You guys are crazy today. The one that's closest is Andrea. You poop it out. You poop it out. Why, Andrea? What did you do first? Okay, digestion. So what did you do first? You swallowed it. Oh, yes, yes. Well, it may have been unknowingly, but now you know knowingly that yeah, every time you swallow, you're swallowing a bunch of stuff that was dripping down from your nasal cavity, and that's perfectly natural. All right, enough of that. I'm not going to the olfactory stuff. That's stuff that you learn in A&P1. Okay, so again, this is basic anatomy. Your nostrils are also called the external nares. That's simple enough. Here's where we start. So your pen. So we look at the mucosa. All right. We have the olfactory, which I'm not going to talk about. That's AMP1 for your olfactory system. But the respiratory mucosa is part one of your essay question. All right. So the nasal cavity has pseudostratified. Remember what that means. It looks like fake layers. It's only one. Ciliated columnar epithelium. And again, it's the cilia that move all the stuff that you trapped in your nasal cavity, and it's going to bring it to the back of your throat, and then you're going to swallow it. The goblet cells produce the mucus. So the mucus and the cilia trap all that stuff, and then you get rid of it through swallowing. All right, so lots of things here. A lot of this stuff is not really important except for a couple little things, all right? First of all, you have what's called the pharynx, and it has three regions. The nasopharynx, referring to your nose, the oropharynx, referring to your mouth, and the laryngopharynx, referring to your throat. All right, so we're going to focus on that. There are a couple other things here that we will go through later on, so I'm not going to make a big deal, but this is primarily one of your anatomy slides to use for the lab practical. All right, so you have this nasal conchae, and again, these are just kind of like folds within your nasal cavity. And we have the superior, middle, and inferior nasal conchae. It's hard to really see this. Superior, it's way up there. But again, what I want you to know for testing purposes is their function is when you inhale through your nose, those little folds are going to get the air to swirl around. And so when that air swirls around, when you inhale through your nose, it's going to hopefully slam all that pollen and dust and particulates into the cilia and the mucus and trap it. That's all I want you to know about that. And the grooves between the conchae are called meatuses. You've seen that question before. All right, don't worry about the sinuses. I'm not going to ask you anything about the sinuses. All right, so again, the pharynx, know the three regions. On the lab practical, I'll make sure that the arrow goes right smack dab in each region so there's no guesswork on whether it's the naso or the oropharynx. All right, but again, it's the same passageway. It just gets a name change as it passes through the respiratory system. Okay, so the nasopharynx, the key here is it still has pseudified ciliated columnar epithelium because we're still trapping stuff. Again, we want to get that stuff down our throat so we can swallow it. All right. That's the only thing that's really important on that thing. We've already talked about adenoids before. You should have been, the auditory tube should have been something you discussed in AMP1. Not a big deal for us. Okay. The oral pharynx. Now listen to me carefully. Who do I pick on? Christine. You with me, Christine?
Yes.
Christine, why did my epithelium change from pseudostratified cilia, simple columnar, into stratified squamous epithelium at the oral pharynx? Why did I transition to stratified squamous?
Is it
Josh?
because like the muscle like changes?
No. Think about this. The nasopharynx and the nasal cavity, that's for breathing air. What happens when you get to the oral pharynx? What's also happening there? Joshua, help her. Food. All right, swallowing food. Yeah, there's going to be abrasion. There you go, Josh. That's tougher. There's going to be abrasion. So you're sharing the oral pharynx with the digestive system. And so when you swallow, and I don't know if I mentioned that before, but that's another thing. When you eat a meal, you're eating a lot of your own cells, right? Everybody knew that? Yeah, okay. So when you, every time you swallow some food, you're going to scrape layers of that stratified squamous off of your oropharynx, and that's going to go right to your digestive system as well. Okay. So yeah, we have that change because we're sharing it with eating food, all right? Then we have the laryngopharynx. Again, we're still in the area where we're still sharing the respiratory with the digestive system, so we still have stratified squamous. And this is my laryngopharynx, just this little area. But right here is when we have the big diversion. We're going to have the big diversion. At this point, when you swallow food, this right here is your epiglottis. This little epiglottis is cool. It's like a little cover. So this is a reflex. You have no control over this. So when you swallow, this epiglottis folds over the trachea. Oops. Over the trachea right here. So the food has to go into the esophagus. All right. And of course, that makes sense. We don't want food or water or fluids to go into our lungs. Who knows what the term is if you get fluid or food into your lungs? Something you're going to hear. It hurts. Well, it can do more than hurt. Well, you could die. Hopefully, it's not that extreme. Pneumonia. Well, let's not. Dry drowning. You guys have great imaginations. All right. It's okay. All right. So you pulmonary something. All right. The term is aspirated. Aspirated. You'll hear that in your future careers. When you have a patient, especially somebody that's been on a ventilator for a very long time, so their epiglottis has been kind of like, because when they put that vent, and I'm teaching you stuff, when they put you on a ventilator, they're going to put a tube down your throat, and it's going to go right into your trachea. So it's basically going to, take the job away from the epiglottis. So it's kind of like just sitting there doing nothing, and it can get rusty. And so anybody that was on a ventilator for an extended period of time, there's threat that the epiglottis won't close like it should, and you can get water or food in there. And it's called aspirated. And hopefully it's not too bad. Hopefully it's not too bad. And it's not the same thing as choking. Choking happens way up here in front of both the esophagus, as far as choking on food. Okay. we're still, again, the key thing for lab practical is we're still stratified squamous because, again, that's still a passageway for food. And then as we drop a little bit lower, we get to the larynx, okay? The larynx. And this is all about the passageway for air, all right? So this larynx includes the epiglottis. And again, a lot of things happen here. We'll look at that. We won't make a big deal. But within your larynx, that's where your vocal cords are for speech. Okay. And here you see the transition. So here's part, 3 of your big lab or your lecture essay question. Because like I said, I'm telling you right now, I'm telling you what's on the test. Track epithelial changes from your nasal cavity to the alveoli. So here we see that the upper portion, superior portion, is still stratified because we're still sharing a little bit with the food business, but the lower portion, now it's all about air, so we're back to our pseudostratified ciliated columnar because we still want to trap all the particles that are in there. Okay, so when we look at larynx, we have lots of different cartilages, all right? So listen to me carefully so you study the proper things. These small paired cartilages I'm not going to ask you about, so you can just ignore those. They're so tiny, they're so itty bitty, all right? You need to know the big 3, the thyroid cartilage, this big one right here. Why do we call it the thyroid cartilage? Come on, this is a trick question. Exactly, very good, Christine. It's the thyroid sits right on top of, or the cartilage sits right on, thyroid gland sits right on top of that cartilage. All right, so that's an easy breezy one. The epiglottis, which is one we just talked about, that's cartilage. That's the little flap that blocks the trachea when you swallow so food doesn't go. And the last one is the cricoid cartilage. And this one down here, if you can see my cursor, is the cricoid cartilage. Otherwise known as somebody. Anybody know what the cricoid cartilage is?
Is that the Adam's apple?
And Daniel gets a gold star. That's exactly what that is. That is your Adam's apple. All right. So yes, for males, because we have more testosterone, this cartilage is more pronounced. It's larger. And so, yeah, that's your Adam's apple. Very good, Daniel. All right. So again, just the big 3, do not worry. Although they're fun to say, arytenoid cartilage, corniculate cartilage, and cuneiform cartilage. But they're, like I said, if you look over here, they're itty bitty tiny things, and we don't really care. All right. So again, the larynx includes your vocal cords. And we're not going to go make a big deal, just be able to identify them on the lab practical. So on this illustration, the white is your true vocal cords. They're the ones that get you to produce sound. And then the ones that are in pink on adjacent sides, they don't have any role. They're just supporting characters. Okay. And again, voice is pretty amazing, evolutionary wise, but it's very similar, a lot of respect to a lot of things. And again, so everything I'm going to say right now is just gee whiz. All right. So you can stretch and make the vocal cords taut so they're nice and tight. And so the analogy, I'm sure everybody at least has seen a guitar, but you know on the guitar, the thin, tight strings make the higher notes, and the thicker, looser strings make the lower notes. And your vocal cords kind of work that way. All right, they can tighten up to stretch them thin and make them tense, or they can loosen them. All right. And of course, we can change the opening as well, because you've probably seen those crazy musicians that blow into different bottles with different openings to make different sounds. Am I only one that's ever seen that? Yeah. Okay. All right. And so, why do men have deeper voices than women? Unlike women, boys, when they hit puberty, get that voice change, that awkward voice change. What's going on there? Somebody that has kids. What's going on? Well, it has to do with hormones, but it's got more to do with specifically the hormone testosterone. Well, yeah, I just said puberty. But why do our voices change physiologically? No one? I kind of gave the answer away already. No one knows. Okay. Well, now you have another. Well, yes, Cindy, it has to do with your vocal cords. But what happened to your vocal cords if you're a boy when you're going through puberty? They get tough. That's not. There we go, Andy. Andy got it. Another gold star for Andy. They get thicker. They get thicker. So they now transition to those thicker. they transition to those thicker strings on the guitar. All right. So when that whatever 12, 13, 14-year-old boy gets that testosterone surge, things start growing, and that includes their vocal cords. So the vocal cords get thicker. So they're like the bass strings on a guitar. So now you know. That's, again, all that was just gee whiz. And it's just kind of funny to watch that, to see a young boy struggle through that area as his vocal cords get thicker and thicker, and the voice starts changing. What is the point of the Adam's apple? Cindy pulls that up out of nowhere. Well, again, it's just like the vocal cords. The Adam's apple is just that let me go back here. That's funny. You should say that. The point of this is to keep that trachea open. All right. So this cartilage here is to try to keep your trachea wide open. The fact that it's bigger and thicker in men is just what we just said, testosterone. All right. So it kind of bulges out more than men. So in men, you can see it. And that's where the Adam's apple comes from. I don't know if it actually comes from like the biblical thing of Adam. I don't even know that. There you go. Yeah. So the Adam's apple just means that your cricoid cartilage is thicker and more pronounced because you're a guy and you have testosterone. Or if you're a weightlifter and you're pumping anabolic steroids. If you ever watch that, I used to watch that kind of stuff. I was interested in that. But the women that do those bodybuilding things, you will see an Adam's apple on them, and then you know that they were taking steroids, testosterones. All right, enough of that. Yeah, very good, Andy. Andy's being clever. It's a protein shake, yeah, with a little charge to it. Yeah. Okay. Yeah. And it's another thing, like I said, that stuff, I don't think that's a big deal anymore. But yeah, like I said, I used to watch those bodybuilding contests and this is when it was perfectly legal to do that. But you would see some of the women contests and they had a deep voice like a man and they had an Adam's apple. And you go, aha, all right, anabolic steroids. Okay, let's move on, guys. All right. So the trachea, like I said, this is what you would call the windpipe. Look what's bolded. So this will be on your lab practice. The carina marks where the trachea divides into the primary bronchi, the two major branches that go to the right and the left. And once again, we're in the trachea and we're still at pseudostratified because we still got to get that junk out of our lungs that we inhaled. All right. We have C-shaped rings of cartilage that, again, just keep keep the trachea open. So if you look at this cross-sectional area, this light blue represents the hyaline cartilage, which we know is tough and whatnot. And that keeps the trachea from collapsing. Beautiful. And over here is just a cute little picture. This may or may not be on your lab practical, but it should be pretty obvious. The pseudostratified with a little cilia on top. All right. And you've seen this before, but again, what you are responsible for, because we said there are 23 branchings, you're only responsible for on your lab practical the first 3. So your trachea branches into your right and left primary bronchi. That's plural. Bronchus would be singular. And each primary bronchus is going to separate into secondary, and then they will divide into tertiary. After that, we quit counting. We don't care. Then we get farther down into the itty-bittiest branches, and just kind of like our vascular system, we go with the oles, bronchioles, just like arterioles. So the bronchioles are really, really small, less than 1 millimeter in diameter. So again, pretty small. And then eventually we get to what's called the terminal, and these are super tiny before we actually enter the alveolar sacs there. So here's the study slide for that big question. All right, so mark it. So we're at the trachea, pseudostratified ciliated columnar. When we split to the bronchi, singular bronchus, we are now just simple columnar. We're done with the with the ciliated. When we get to the bronchioles, we are simple cuboidal. Smaller cells, smaller diameter. Everybody got that? I hope you're writing down the answer to one of your big questions. All right. Okay, great. All right. The bronchioles have smooth muscle in it, so that's where a lot of your what we call bronchial dilation and bronchial constriction come in, like we talked about during the fight or flight response. Under sympathetic response, we're going to open up those bronchioles to get as much oxygen and air we can. The parasympathetic wants to constrict them. Beautiful. Any questions so far? All right, beauty. So this is what's remarkable. As important as lungs are, the anatomy is nothing. We literally have a right and left lung. Here's always an interesting thing as a biologist and an evolutionist. I always remark, and I'm sure I mentioned that when we talked about the vascular system, is we're not symmetrical, as you would think. We're not symmetrical. We're not exactly, mirror images on right and left sides. So on the right side, we have 3 lobes. And again, it's really simple. Superior, middle, and inferior lobes. How easy is that? The left lobe, a lung, has just 2 lobes, a superior and inferior. So again, that's just weird. Another little asymmetric thing is, and this is important on your lab practical, you have a little notch, cardiac notch. It's called a cardiac notch. Why? Again, this is almost a trick question. No, not your pulmonary. Andy, Nada, and Bucola. That's where your heart sits. It's nestled. Your heart sits nestled right in between the 2 right and left lungs. All right. So it's got a little notch for room for the heart. Okay. Other simple things. We have an apex. All right. We have a base. The only other thing I want you to know is the hilum. The hilum, where my cursor is, that's where the trachea branches into the right and left primary bronchi. So the bronchus goes in there. It also has the arteries, the veins, and the nerves that also enter. So this is like an entranceway. So the hilum is the entranceway. Okay, beautiful. Again, just a little anatomy. And you've heard of the pleura before, or you should have an AMP1, but you have a membrane that lines the cavity. And this is kind of important for us here when we get into the physiology. So the parietal pleura lines the cavity, the thoracic cavity. The visceral pleura lines the lungs, direct contact. So you have what's considered a pleural cavity, but I always hate that because it's really not a cavity. It's two membranes that are tightly closed together with a little bit of fluid in between for lubrication. All right. And that'll make more sense when we get there. All right, since we branch, we get to the terminal bronchioles, and then from there, we get to the respiratory bronchioles, and now we enter what are called alveolar sacs. An alveolar sac contains a lot of little alveoli. These are little itty bitty sacs where the gas exchange is going to happen between the capillaries and the alveoli. All right, and so again, nothing really significant. Like I said, looking at a piece of lung tissue is boring as hell because it's just simple squamous. So when you cut it and slice it and treat it, it looks like this mess over here. All right, so nothing really important with that. All right. Okay, so now we're down in the alveoli. These are the itty bitty sacs, air sacs, if you will, and we have the sac itself is made of simple squamous. Again, we want simple squamous because we want gas exchange to be very simple. All right. And then we have some cells scattered throughout there that provide us with a couple protection. We have some macrophages that are going to eat whatever you inhaled that you shouldn't have. And something called surfactant, which I will explain a little later. All right. The lungs are very elastic, okay? A lot of elastic. These little alveoli, alveolus singular, are like itty bitty balloons. They expand and then they contract, all right? So when you take a big, deep breath, every single one of those little alveoli expanded like a balloon, all right? Your lungs are extremely elastic, and we'll talk more about that in a little bit. And again, there's nothing really significant about this slide. It's just showing you where if you look at a transverse section, you would see the diaphragm, which is, again, a flat sheet of muscle, which is the most unique muscle. Why is it unique? Come on, critical thinking. What makes the diaphragm different than any other type of muscle you have in your body? Well, the way they contract, not quite what I was looking for. Not quite. No, not the muscle fibers. It has to do with control. Does that help anybody? You don't, Joshua? You can't control your diaphragm? Joshua, you don't think you can control your diaphragm? Yeah, you can. Okay, Christina and Christine, those are all pretty clever little things. What I wanted to hear, Joshua was kind of onto it for a second there. That's the only muscle where it can be automatic. You don't sit there and think about breathing. So it's automatic for your normal breathing rate when you're doing other things, but you can control it. You can hold your breath. You can take a deep breath voluntarily and blow out your birthday candles. So it's the only muscle in your body that is typically automatic, but you can override that when you want to, like I said, blow out the candles on your cake or hold your breath or whatever you want to do. Okay. That was all just gee whiz. All right, so now we're getting close to our physiology. So again, I expect you to know the definition of pulmonary ventilation. This is just getting air in and out of your lungs. That's it. It's the first part of the entire respiration aspect. But ventilation just means getting air in and out of your lungs. All right, inhalation, exhalation. And again, that is the function of your intercostal muscles and your diaphragm. And this is where I was alluding to earlier. So to breathe in, the external and internal intercostal muscles lift your rib cage up, and the diaphragm pulls down. And this, again, simulates the bellows thing that I was talking about, where you expand your thoracic cavity and then you contract your thoracic cavity. And this is, again, gee whiz. We're all kind of like over COVID now. At least I am definitely way over COVID. Everybody doing okay with the COVID thing? I still have some friends. I still have friends that are getting COVID. I don't get it. I really don't get it. I have lots of friends. I'm like, how are you still getting COVID? I don't. Yeah, Deani, I have never had it. You know, and I guess I'm in a very small minority that had never gotten it. I've had friends that got it 2 or 3 times, and you know, and I may have. Yeah, Christine, like I said, I couldn't tell COVID from the allergies I get all the freaking time. Yeah, and the person that just took over for me as department chair got it right the very first week he took over for me. I'm like, oh gosh, so now I had to continue being department chair for another week because he had. I'm like, how the heck? Geez, I went to South by Southwest parties. I went to like 3 parties during South by Southwest. Crowded bars. No one's wearing a mask. And I just said, okay, now I'm going to get COVID, pretty sure. And so, yeah, Monday or Tuesday, I don't feel great. Yes, Christina, I did say that earlier. I did say that. I just want to know what it was like. And we already had that conversation when we talked about the immune system, because the way I looked at it is I already had my okay, Andy, I'll keep that in mind. You have to make our registration. I didn't think about that. But we had this conversation in the immune system. I figured if I got COVID, that would just amp my immune system up even more than it is. But nope. So yeah, ACL is, yeah, I'm sure. Do I have to go to ACL in November just to get COVID? I don't know. Anyway, all right. You got an HEP? You guys are crazy. Well, like I said, I think there's only a handful of us that are in the minority that did not get it at all, ever. And like I said, once I got my second Pfizer shot, I dropped the mask and didn't care anymore. Okay, let's press on, folks. Love the comments. And Andy, I'll take your advisement next party I go to. All right, here we go. Oh, Samantha, did you just make that up? Or is there such things as COVID parties where everybody tries to get it? No way. That's a real thing? I had no idea. There are COVID parties. Wow. God, I just didn't get the invitations. I don't know. People are crazy. Okay. Good comments, folks. All right, here we go. Now, we're into the physiology. And there's about 4 laws that you have to know. All right. The first law is Boyle's law. And these all the laws will be on the test. All right. So Boyle's law is super simple, and you've experienced this throughout your entire life. As volume increases, pressure decreases, and vice versa. It's an inverse relationship. All right. So if the pressure increases, the volume decreases. And this is what this little illustration is trying to show you. And when we talk about pressure, we're talking about atoms. We're talking about air molecules. They're bouncing around. If you give them plenty of room, they can freely bounce around. The pressure's low. When you compress it, the volume, then there's more pressure because now they're bouncing around like, I can't even use any of my analogies. Do any of you have ever heard of the original video game Pong? Jessica, that breaks my heart. You've never heard. That was the very first original video game. Pong. Anyway, well, like I said, that's the ball that goes back and forth, and it goes faster and faster and faster. All right. Anyway, like I said, my analogies are dinosaurs now. All right. So again, all you have to tell me is that there's an inverse relationship. All right. Okay. We're going to put that to practice here in just a second. All right. So right now, you're responsible for knowing what atmospheric pressure is, which is 760 millimeters of mercury. And again, I've already explained where the millimeters of mercury came from when we talked about blood pressure. And so that's standard. That's what I mean by standard in science is that means it would be 760 if you were at sea level at 26 degrees Celsius. You don't need to know that part of it, but if you ever watched weather on the news and they said we're entering a high pressure area or low pressure, because this can change with the dynamics of the atmosphere. But for science, we always go with the standard. What would it be like if you're at sea level at 26 degrees? That's not important. Just know 760. In your lungs, we go back and forth between this atmospheric pressure and your lung pressure. Your lungs are always trying to equalize. And I'm going to turn to my whiteboard, if you will, in just a second. So the only thing that's really, truly important right here is you have, again, this is exaggerated. So here's my parietal pleura and my visceral pleura. And in between is our pleural cavity. But again, this is exaggerated. These two membranes, the visceral and parietal, would be right next to each other, with just a little bit of fluid in there. But this is what we call a negative pressure. It's like a vacuum. It keeps the parietal and the visceral in contact. They stay together. And that's extremely important because, like we said, with the intercostal muscles and the diaphragm, you're expanding your chest cavity and you're contracting your chest cavity, and you want the lungs to follow the cavity expansion and contraction. All right. We have two different names for the pressure that's in your lungs. So one, and I hate when they do this to us. So you have intrapulmonary pressure. That's the pressure that's in the lungs. Another slide also causes the intrapulmonary pressure. But again, this is the pressure that's in your lungs. And then the pressure that's between the two pleural membranes is less than that to create a vacuum. All right, so here I'm going to transition to my whiteboard, and this is going to cover the next 4 slides. So you can just skip the next 4 slides because I'm going to explain it with my amazing artistic skills. So here we go. Give me a second. All right, beauty. Everybody got it? We're good? All right, beautiful. Okay, so I'm going to draw a set of lungs. So as best as I can. Boom. There's my trachea. All right, that's okay. That's good. Now, remember, our atmospheric pressure is 760 millimeters mercury. This is what's in the atmosphere. So this is where Boyle's law comes into play. All right? So when I take a deep breath, I'm expanding my thoracic cavity, I'm stretching it out, and the lungs are going to follow. Therefore, I'm increasing the volume in there. Now, originally, for just in between our breaths, we equalize. So originally it was 760. I'm going to put this over here really small. All right. But I expanded, I increased the volume. What does that do to the pressure? Decrease. Very good. So the pressure, when you take a breath in, is going to be 758. Not a whole lot, but plenty of difference so that air, and this is just like diffusion. We go from high pressure to low pressure. High pressure 760, low pressure 758. So air is going to go in the lungs. I just inhaled. Now, like I said before, your lungs are very elastic. So when I relax, because of all the elasticity, the lungs are going to contract. And this is not working very well. This is why you can't erase. So now my lungs are contracting. My volume goes down. The pressure does what? Okay, very good. You guys are onto this. So now I'm at 762. This never changes. This is that's the entire Earth's atmosphere. So that number never changes. All right. So now I'm at 762. So I go from 762 to 760, high to low. So the air exits my lungs. Boom. Everybody got that? Basic, simple mechanics of the lungs. All right. Beautiful. All right. Great, guys. Great. All right. Beautiful. And that's what these slides say. The only thing on here is, like I said before, is between the pleura, the membranes, it's a negative pressure. So it keeps the two membranes held together like a little vacuum. You can break that vacuum if you get stabbed in the chest. What happens next? What happens to your lung if you puncture these pleura and you release the vacuum? What do we call that? Anyone?
It collapses.
Okay. Yeah, collapsed lung. Collapsed lung. Anybody know the medical term for that? Okay, it's called a pneumothorax. Has anybody ever heard that term before? Yeah, it's not the easiest thing to. Yes, it starts with a P and then an N. No, 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 no. That's if your trachea is blocked. If you're talking about putting a little knife or whatever into the trachea so they can breathe, you know. Oh, this, well, what you're supposed to do, and this is just my military training because we had to learn what we called self-aid buddy skills, is you just need to seal that whatever that wound was. You need to seal it, and hopefully that the lung will seal back up. But yeah, we'll talk more about that in a little bit when we get there. But yeah, so a collapsed lung means you broke the seal. There's no vacuum to hold the visceral and parietal pleura together. So it just kind of, your lungs are small, folks. They are always expanded in your chest. But if you took them out of your chest, they'd be about 1/3 the size they are. So they're always stretched in your lungs, always stretched. I mean, to be honest with you, your lungs are about the size of your fists if they were outside of your body. But hopefully that will never happen. Okay. No, Jessica, you got it backwards. They would be way smaller if you took them out. Okay. All right. So, I mean, look at yourself, look at your chest, kind of measure where your lungs, the size of your lungs are. If you took them out, they would shrink to, like I said, the size of your fists. All right. Because you've lost that elasticity. Well, you got the elasticity that recoil, but you have when they're out of your chest, they're not expanded because, once again, of those pleural membranes keeping them expanded. So yeah, if you ever get the chance, and some of you will, if you become a nurse, you can go. I know this is going to sound kind of gross, but how many have heard of what they call as an organ harvest? I got to go to one. Christina, you went to an organ harvest? Okay, you've heard of it. All right. So yeah, as a nurse, you could have opportunity to go to one. It's usually when somebody is brain dead and they have a donor card that says, I'll donate my organs. So like I said, it sounds kind of crude, but it's extremely important. So you have somebody that's brain dead for whatever reason. So they're going to go and they're going to take the heart and the lungs and the kidneys. They're going to take everything out and hopefully give it to patients that need those things. And I just bring that up because, like I said, the first time I saw that, when they took out the lungs, I was like, oh my God, they're so small. But anyway, I'm getting off track here. All right, so that's all these three slides said was what I just covered in my little drawing here. So let's go back to our slides. Okay, so we're still talking about ventilation. All right, and there are factors that we've kind of already talked about. Resistance is always the big thing for any kind of flow, whether it's blood flow or airflow. All right. So as we learned in the vascular system, if I decrease the diameter or the radius, I increase resistance. All right. We also have to have compliance. And this is, again, compliance and elasticity are a little different. Compliance means the ability to stretch, to just relax and let things happen, let things expand. And so they need to be able to distend. And one of the biggest concerns is surfactant. And this is kind of a complicated, I'll try to make this as simple as possible. We all know that water is polar. Water molecules attract other water water molecules. So when you have a surface that is covered with water, all those water molecules are attracted to each other, which causes surface tension. That's why those little water bugs can literally crawl across the water. Your lungs have a lot of fluid. So water is constantly trying to keep them together, and you need to be able to break those water molecules apart to allow those alveoli to expand like a balloon. And so we have something called surfactant that just separates them from that. The elastic recoil, again, we need elasticity. So we have compliance, stretch. When I inhale, and then when I relax and exhale, I need that elastic recoil to decrease the volume and expel the air. Don't worry about this slide right here. This is more math than you guys need to know, but it's just trying to tell you that, we have something called surfactant, which basically just keeps the water molecules apart so they don't have any tension. They're not inhibiting the ability for the sacs to expand. And this is your gee whiz fact. When you have a preemie, a baby that's a little early, the cells that produce that surfactant aren't really developed. And so it's obviously one of the first things they're going to do with the preemie is put them in an oxygen tent because, again, their ability to ventilate is not great. Any questions so far? All right. And I'd like to think now, even though, like I said, COVID's pretty much over, but if you remember 2 years ago, 2 years ago, it was all about ventilators. And I was surprised at how many people really didn't know what a ventilator did. And so all a ventilator did really was they stuck the tube down into your lungs and they helped you get air in and out of your lungs. That was it. And I'll try to explain why that was critical and why that was the number one reason people died of COVID was because their lungs filled with fluid. And that will be our discussion on Wednesday so that you already got the immune part. Now you know the physiological medical part of COVID and why it was so horrible. This is my joke slide because there's lots of commercials that talk about COPD. Again, to me, this is just funny because COPD is the most generic thing in the world. There are dozens and dozens of things that cause your lungs to be obstructed or increase resistance. So you may have seen those commercials on TV about COPD, but like I said, it's so generic. So bronchitis. And there's a generic thing. What does itis mean, somebody? Inflammation. Very good. All right. So bronchitis is, again, extremely generic. Viruses cause bronchitis. Chemicals cause bronchitis. Bacteria cause bronchitis. So, that's extremely allergies. Yes, very good, Christina. Allergies cause bronchitis. So that is so freaking generic. It just means that your bronchioles are inflamed. All right. That's all that means. And there are a lot of reasons for that. Emphysema. Yeah, Christine. Yeah. I used to get bronchitis for everything when I was younger, but not anymore. And emphysema, that's another thing that, like I said, that's usually from bad things like smoking or inhaling toxic chemicals like chlorine, whatnot. All right. So my whole point is all these things are somehow affecting your airflow to your lungs, affecting ventilation. Emphysema is probably the absolute worst because you're destroying the alveoli and you're destroying the elasticity. So normally, listen to me carefully, when you're normally breathing, you are actively stimulating and contracting your intercostal muscles and your diaphragm. When you normally exhale, just a normal exhale, all you do is relax and let the elasticity of the lungs contract the lungs and force the air out. If you lose that elasticity, then, oh my God, it's a horrible thing, because now you have to forcibly inhale and you have to forcibly exhale. And obviously that can be exhausting. And so that's why most of them have to be on a O2 supplement. O2 supplement. All right. And again, the last one is just gee whiz, because I want you guys to know stuff that you can take with you. What's the difference between bronchitis and asthma? Anybody? We already know that bronchitis is just inflammation of your air passageways, which can be caused by viruses, bacteria, allergens, you name it. When you have bronchitis, you have swelling, so the air passageways, the diameters of those have restricted, just like we learned in our vascular system. We have reduced the radius, that increases resistance. So yes, that sucks. That's due to the inflammation of those walls of the bronchi and bronchiole. What's asthma? Who knows what asthma is? Okay, not quite. Asthma isn't not for cells for inflammation. Anybody else want to help Christine here? All right, so this is just your gee whiz thing. Asthma is, and we don't know all the aspects, but it's something triggers your bronchiole to constrict. So that's the smooth muscle. So that's like, again, this is all just gee whiz. I thought you might want to know. So bronchitis is swelling, which reduces the air passageways. Asthma is an actual trigger that causes the smooth muscle in the bronchioles to constrict. The effect is the same. But again, when you have somebody with asthma, they take an inhaler. What's the number one ingredient in an inhaler? Anybody know? Which is? Thank you. Very good. Who said that first? Andrea? Yeah, it's a steroid. So yes, like I said, I'm trying to give you applicable things. So albuterol is a steroid that acts just like adrenergic receptor, where it's going to cause the bronchial dilation, just like which adrenergic receptor? For 2 gold stars, which adrenergic receptor causes bronchial dilation? Christine, Diane, yes, 2 stars for both of you. Beta 2s. Excellent. That makes me feel really, really good. All right, let's move on. All right, so respiratory cycle. So again, we are talking about we're under parasympathetic influence. We're just breathing normally. Nothing exciting is happening in life. So I inhale and I exhale. This is called our tidal volume. All right. And our tidal volume is about 500 milliliters, or half a liter. This is where the metric system comes into play, because that's all we're going to talk about. So a half a liter. So think about your liter of Coke or Pepsi. About half of that is what you inhale and exhale. That's called your tidal volume. All right. Now, if we were face to face, sadly, this was one of my fun ones, we would do what we call spirometry, which means in lab, we would have you hooked up to something that covers your face and hooked up to a computer and a transducer, and we could look at the flow of air in and out of your lungs. And we'll talk more about this tomorrow when we try to discuss our lab. All right, so this is what we call a spirograph, which is funny. I don't know who the oldest person in this class is. Do I have any? You don't have to answer this because it's kind of private. Do I have anybody that's over 40? No one's going to admit that. Okay. Wow. All right. So Jennifer's 23. I know a lot of you are young, but I was hoping there was somebody that remembers the old toy called Spirograph. But look it up. Like I said, I'm getting old. All my Christine has a old self. Okay. But there was a toy thing when I was a kid, the Spirograph, which is it's not even worth it. Maybe discussing it. Christina says, okay, Christina, describe it. So they don't think I'm crazy, Christina. Describe what a spirograph was. You've seen those. The stencil thingy, yes, Diane, yeah. Yeah, where you pen and you had to rotate it and it had different designs and you got some, yeah, the stencils. Okay. What does this have to do with our class? Nothing. It's just, it was called a spirograph, but in our physiology, this is spirograph, what we're talking about right now. Okay, so Nada remembers. Yeah, you just drew a design, and it was always some nice little cool artsy design that you would create. All right. So what we would have done in class is you would have picked one of your student peers in your class, and we would have strapped them up, and we would ask them to slowly just do their normal thing. They'd take an inhalation. Again, tidal volume, 500 milliliters. That's testable. Everything on this slide is testable. You know, I would like to think by now, folks, every graph is on the test. Every graph. And like, because I was kind of a little disappointed. Well, yes, Christine, I like graphs because science is all about graphs. Why do scientists like graphs, Christine, since you brought it up? There's an old saying that's very similar to that. Why do scientists use graphs?
Because it's easier to visualize what's going on.
Okay, very good, very good. It's very similar to that old phrase. Who can finish this for me? A picture is worth 1,000 words. Very good. Cindy, 5 words? Cindy, you're hilarious. That would be like a stick figure, I guess. Yeah. So a graph tells you a ton of information in something that you can visualize, as Andrea said. All right. So yes, every graph that is in my course is going to be on the test. All right. And I was kind of disappointed because I pretty much emphasized that the Wiggers diagram was going to be on the test. But some of you, anyway. Okay. So here we go. So yes, this is going to be on the test. Of course it will, Jennifer. I just said graphs are on the test. So this is going to be on the test. So I want you to kind of just visualize what's going on. So you have one of your students and they're strapped to a thing that's on their mouth and we're monitoring their breathing and their volumes. So they take a nice normal breath, inhale 500, exhale 500, inhale 500. And then what we would do is check what we call their expiratory reserve volume, ERV, which simply means how much more air can you exhale after you've already taken a normal expiration. Did everybody follow me with that? Okay, so if you look at this graph, we have a normal inhalation, a normal exhalation, normal inhalation, a normal exhalation, and then I say, okay, go, and you're like, and expel as much air as you possibly can. That is your ERV, and it's about 1,100 milliliters, or a little over a liter. Then you would have taken a normal breath in, 500 milliliters in, 500 milliliters out, 500 milliliters in. So now you've taken a normal inhalation, and now you're going to inhale as much air as you possibly can. You're about ready to blow out all those candles. This is your inspiratory reserve volume. Excuse me, I just got that completely backwards. Well, yeah, you're going to, but you have to get that air in. So you take a normal inhalation, and then you're going to inhale as much air as you possibly can to the max. This is your inspiratory reserve volume. Everybody with me so far? So now you're here, you're maxed out, your lungs are completely filled, and now you're going to blow out those candles or blow up one of those skinny little stupid balloons. So now you're going to exhale everything. Exhale, exhale, exhale all the way down. You just got, here was your max air in your lungs, and you just got rid of them as much as you can. That is called your vital capacity, and that's at 4,600 milliliters. So that's why I use the birthday candle thing. Take a deep breath. You're at your max inspiratory reserve volume, and then you exhale as much as you can. You're blowing out the candles. You got all the ones. And for somebody like me, that's a lot of candles. All right, that's your vital capacity. Okay, don't worry about functional residual capacity. Not going to ask you that. Not going to ask you about inspiratory capacity. Yes, Andrea, I know. You guys would have loved to do this, but like I said, don't get me started. There are some labs that we should really be in class to do, and this would have been one you would have enjoyed. But oh well, here we are. Okay, so for lab and lecture purposes, you don't need to know about functional residual capacity. Christine, you don't know that. Andrea, you know what? I have access to our labs. If you guys want to do it, it would have to be completely optional, but I have access to our labs, and we could do this if you guys wanted to. Okay. Well, like I said, having been the department chair for 12 years, I have access to everything. If some of you want to do this, I can make that happen. It's, so we can discuss that later. Let me finish this up real quick. Okay, so maybe extra credit. Yeah, well, I don't know. Well, yeah, you don't have to volunteer to do it, but you can watch it. I'll think about the extra credit, but I have to be very careful because it's optional, and I don't want to people that may not want to do the optional thing, and then you have to understand. Then somebody will complain, "Hey, I couldn't go, and now somebody's got more points than me." Okay, but anyway, let's move on, and I will think about opening up the lab, and we can do this. It's a very easy lab. It's fun, all right, and it will tell you more about actually how your lungs perform, because this is what we do. This spirogram is what we do for patients that have lung problems. So you are responsible for these numbers, all right, for your test. I'm going to jump here real quick. You're responsible for these numbers, these volumes, all right? Again, these are averages. And if you have, there's a big range. If you look at your inspiratory reserve volume here, and the reason there's a huge range is it depends on how big you are. If you're petite and you're small, you're going to be down here at 21. If you're a very large person, you could be up here. So on the test, you have a lot of leeway. As long as you're in the ballpark, you're going to be fine. As long as you're in the ballpark, you're going to be fine. All right. So let me go back here. So I finished up with the vital capacity. That's as much air. You take the biggest breath you can, and that's as much air as you can expel. Boom. That's your vital capacity. That'll be a test question. Now, even if you expel everything you possibly can, you have what's called the residual volume. This is the air that you cannot get out of your lungs. Why? Why wouldn't you want that air out of your lungs? Simple question. Why wouldn't you want Joshua? Joshua's always going for the dead. So you won't die. Okay, Andy, that's good, Andy. Yeah, if you got that 1,200 milliliters, then your lungs would collapse. So that never leaves because all those little itty bitty sacs would all be deflated, and that's not a good thing. That's not a good thing. Do you remember? I showed you the G videos, right, guys? Yeah, and that was a big concern. Is if you didn't do that breathing thing that I told you about, and you exhaled under those high G forces, all your little alveoli would collapse, and that sucks. Now, some of you, maybe all of you, have experienced a situation where you did expel most of this residual volume. What am I talking about? What am I talking about? There's a certain situation where, very good, Andy, very good. Get the wind knocked out of you. All right. I don't know how many of you have experienced that. The first time I did, I was like 12 years old. I was climbing on a tree, and I literally fell out of the tree and landed straight on my back. And I thought I was going to die. I was like, ugh! How many have had the wind knocked out of them? Christina had it with a car accident. Yeah. Cindy fell off a trampoline. That'll do it too. Yeah. Jessica flew backwards off a swing. I love these stories. That's so cool. So yeah. Dog fell on me. Oh my God. Got it in the stomach with a soccer ball. Oh my God. I need to copy all these. These are awesome. But yeah, so you literally, whether it was a dog or a swing or a trampoline, you literally knock that residual volume out of your lungs. And yeah, it's kind of scary in the beginning. The first time I did that when I was 12, I thought I was going to die. I'm like, okay, I'm dying at 12. Shit. Excuse me. But yeah, you just have to wait a little bit until you get that air back in there and get your lungs inflated again. All right. I love these stories. Great. All right. So you are responsible for test purposes to know these ranges here. Again, don't worry about the, just for now, but like I said, this is recorded. I don't care about this. That's a thing that they do for somebody that's got lung disease, but we're not going to worry about that. So these are the things that you need to know right here. All right. Everybody got that? And on the previous slide here, there's the little box that tells you the volumes over here. Okay. And I expect you to know that. Don't worry about this. This is, to me, is like trivial. Yes, there's dead space. Yes, there's air in your bronchioles and your bronchi that are just sitting there. So I don't care about dead space. So just ignore that. Any questions? We're stopping right here. We're stopping right here. All right. Okay, so I'm gonna try something different. Because I wasn't really happy with the first test, and I'm sure a lot of you weren't either. All right. So I'm gonna try something different because I do want you all to succeed, but you gotta put the effort in. So let's just do this little thing real quick. As of today in this lecture, I will pick on who first. Who do I pick on? We have people, I have my people that are always participating, and then ones that are just going along for the ride and not really participating as much as I'd like them to. But let's see here. Christine.
Ah, man, you always pick on me.
Well, why do I do that, Christine?
Because I'm awesome.
Tell them. Why, Christine?
Because I'm smart.
It looks like Okay, I've been exposed. I'm sorry, Christine.
My secret's out.
Secrets out. Everybody knows. Oh my God, that's funny. I hope you're not offended, Christine. Okay, Christine. When you go to study, what are you absolutely sure is going to be on the test? Give me one thing that you're absolutely sure is going to be on the test.
For this exam,
Yes. Coming up.
so describe the changes in mucosal inner lining from
Nailed it.
from the
That's good
nasal to
enough.
the alveoli.
Very good. Nailed it. Nailed it. Good. All right. Everybody hear that? Everybody write that down? Okay, who do I pick
There's
on?
something that I found was really helpful.
What's that? Yeah, help your
So
class
I
out.
like to print out the slides, like 3 slides per page. And like as you're talking, I'm writing and highlighting and making notes. And then when I
Well,
go
yeah.
back through it, I make like tabs based on what you say are important. And so when I go back to review, I make sure to highlight those tabs. So I'm like going over the important things and not really trying to memorize everything, but just kind of like pull it all together and what I think you would put on the exam.
Well, Christine, you just nailed it. Did everybody get that? That's genius there, Christine. That's exactly what I'm talking about. All right. That's a great strategy that you have. Okay. All right. So the next question. Let's see here. Who do I ask? Okay. Bukola, give me something.
Yes, sir. I'm using my phone at the moment. My Wi-Fi is down. So
Oh no. Okay.
okay, sir.
Okay, so you can't tell me what you think is definitely going to be on the test that you're going to study?
On the test, the graph will be on the test.
Okay,
Boy's
good.
law, relationship of
That's
Boy's
all you
law.
need to say with the graph. We're gonna share. We're gonna share.
Can you
All
hear
right.
me?
So yes, I hear you, and yes, the graph that we just presented will be on the test. So that's excellent. That's excellent.
Yeah, and you mentioned Boy's law.
Well, okay, no more. Let's give somebody else a chance to discuss. So far today, epithelial mucosal changes through the respiratory system, the spirograph, good. And there's one or two more things, and let's pick. Wait, let's see what. So Deani says what? I use my iPad, but I need to not think too hard about what to study. Well, again, like I said, if you're really paying attention and taking notes, you will know what's going to be on the test and what you need to study. All right. So there's just a couple other things that I mentioned that I want you to know so far. Just a couple. And yes, Bukola already said that. Okay, Diani, pick one. What is it, Diani? Boyle's law. Yes, Boyle's law. That's the first of 3 more laws that you have to know. And that's actually the simplest one. Okay. That's the simplest one. Anything else? Review these slides and yeah, Andrea, those are just lab practical things. Yeah. Yes. Atmospheric pressure, of course, that's 760, but that'll go into Boyle's law. Respiratory volumes, very good, Andy. I expect you to know all your respiratory volumes. So you're going to get a blank spirograph there, and you're going to tell me that what's IRV, what's ERV, what's TV, and